So now we come to the next parameter, which is the input impedance. We saw one parameter which is called the field zone, radiation field zone. And now we come to the next parameter, which is called the input impedance of the antenna. Now for the input impedance of the antenna, as you know, the antenna by definition we have seen in the antenna. What antenna does is we have a guiding structure. The antenna is connected to a guiding structure and antenna like this. Now here the guiding structure is again connected to some circuits from which the power is generated. The whole thing is shown here in the blue box, which is shown as the transmitting. TX is for transmitting, RX is for receiving. So transmitting or receiving circuit. So the circuit from the output of the circuit is connected to the antenna using a guiding structure. Now this circuit is connected to the antenna. The output of the circuit is connected to the antenna. As you know, in the electronics, the output from a circuit is given to a load. Here the antenna acts as a load. So, at the input terminal of the antenna is interfacing between wave phenomenon on the outside of the antenna and the circuit phenomenon on the left side of the antenna. The antenna input characterization uses impedance circuit parameter, because at the input, if I remove the antenna, so when we put the antenna at this input point, it is as if we are putting a load across the circuit, so the circuit is delivering power to a load. So whatever input impedance is seen at the input point from the circuit, by the circuit sees input impedance Zin, which is the Zin is the input impedance of the antenna. So the circuit sees a input impedance Zin or a load impedance Zin connected across its terminals, output terminals. So if we remove the antenna and across that port, so if we put an impedance which is equal to Zin. So suppose antenna impedance is equal to 50 ohm. So if we put a load of 50 ohm, or antenna impedance is equal to 47 plus J53. So if we put a load there of 47 plus J53, so this is equivalent to a load which was offered by the antenna. So that the impedance of that load is called the input impedance of the antenna. Similarly, that is what is shown here. You can, instead of antenna, the second figure, the bottom figure shows you, we have replaced the antenna with a load whose input impedance is Zin, where Zin is the input impedance of the antenna. So the load has input impedance Zin. So what happens is, when we have antenna, the nearby objects and antennas, if you have nearby objects near the antenna, nearby objects means objects near the antenna. If you have an object then you move the object. You add some other objects. They will be affecting the electromagnetic field, because electromagnetic fields gets incidented on those objects and gets reflected. When they get reflected, they go back to the antenna. Antenna acts as a receiving mode, so that power goes back to the antenna. So if you have more objects, more power will go back. Less objects, less power will go back. Position of the object changes, the power will change according to the radiation pattern. Therefore, nearby objects and antennas near this antenna, the antenna that we have connected, they will affect the input impedance, because impedance in terms of power you can define impedance always. So because of the power, so they affect the input impedance of an antenna, or simply the antenna impedance. So our discussion here that we discussed about ZIN is assuming the isolated antenna, which means there are no nearby antennas, there are no nearby objects. Antenna is isolated from all other antennas or all other objects near it. There is no antenna or objects near the main antenna that we are using, or that is connected to the circuit, transmitting or receiving circuit. So the antenna connected to the transmitting and receiving circuit is alone. There is no other nearby object. In that case, whatever is ZIN for the antenna, you take that ZIN and replace that load. So that ZIN is called input impedance of the antenna. That impedance, the load impedance, is called the input impedance of the antenna. Now we will come to the next parameter, which is called the radiation pattern of the antenna. A radiation pattern gives us the distribution of the electromagnetic field created or generated due to an antenna in the free space, in the space around it, in the far field zone. As we have discussed, there are three zones. One is near field zone, one is radiating near field zone, one is reactive near field zone, then we have a far field zone. So in the far field zone, the distribution of the electric field is called the radiation pattern. So this shows a typical radiation pattern with using the coordinate system. This figure shows a typical radiation pattern using the coordinate system. And the angle from the z-axis towards the xy plane is theta. The angle from the x-axis towards the y-axis is called phi. The plane xy plane is called the azimuth plane. The plane perpendicular to the azimuth plane is called the elevation pattern, elevation plane. Now, in this space, let us consider an area, small area. So in that small area dA, that will be equal to r square sin theta d theta d phi. What is r? It is the distance from the center, or distance from the origin, or distance from the location of the antenna to a point in the space in the far field. So that is what is dA. dA is equal to r square sin theta d phi. The rest of the things are not important. Now, what is the radiation pattern definition is? This is angular variation of the radiation in the far field due to the antenna. Example is directive, single or multiple narrow beams. So directive means in a particular, it is maximum in a particular direction, then it goes down as you go away from that direction, the intensity keeps on decreasing. So it is directive. If it is maximum in a particular direction, it is said to be directive. So directive single beam or multiple narrow beams. This means if we have one beam, single beam means one beam, so there is only one maxima. If there are multiple beams and multiple maxima of same amplitude, multiple maxima of of same or nearly equal amplitude, then those are called multiple narrow beams. Multiple beams comes from that. But if you have a single beam, single beam with a maxima, then there are other beams with maxima, but the amplitude of maxima are different. So you have one beam with a large maxima, other beams with smaller maxima compared to those to that largest maxima. Then that is also a single beam pattern. That is not a multi-beam pattern. Those beams are called side lobes or side beams. This beam is, which has the largest maxima, is called the main beam. So you should have only one main beam or multiple main beams. If there are multiple main beams, then it is called a multiple narrow beam antenna. If you have one main beam, then it is called a single beam antenna. Then the other example is a omnidirectional antenna. As we discussed, isotropic antenna. In the isotropic antenna, radiation is equal in all directions, all 360 degree, in theta plane, in phi plane, everywhere it is same. That is called isotropic antenna. Omnidirectional is, it is same in one plane. The radiation in any one plane, you take any plane, usually we take the azimuth plane, which is the XY plane. In the azimuth plane, the radiation is uniform. So uniform radiation in one plane, that is called the omnidirectional antenna. This is a physical antenna. Omnidirectional antennas are physical antennas. We will consider dipole antenna. We will discuss dipole antenna. That is an omnidirectional antenna. Then stepped beam antenna. Stepped beam antenna means we design the antenna or design array of antennas. Array of antenna means n number of antennas. Many antennas, we design these locations of the antennas and phasing of the antenna in such a manner that we will get a main beam in a particular direction. The maxima of the main beam will remain almost constant over a angle. So that is what is called a stepped beam. So in the stepped beam, we design of the shape of the main beam as per our choice. That is what is a stepped beam. So shape of the main beam can be designed. If the shape of the main beam is designed, then that beam is called a stepped beam, stepped main beam antenna. So these are about something on radiation pattern. Then we'll come to the main lobe. In the radiation pattern, the main lobe. The main lobe is, it shows the angle with the highest radiation intensity. As I told you earlier, main lobe or main beam. This is called main lobe or main beam. In 3D, it is called lobe. In 2D, we call it the beam. So main beam or main lobe. This gives the angular region with highest radiation intensity. This contains the direction of maximum radiation. The cause for this is the fields, electromagnetic field or electric field, particularly electric field, because once we know the information about electric field, we have the information about magnetic field. E and B are related. So particularly electric field. The fields from various parts of the antenna, they cause the main beam. Now when there are various parts of the antenna, means various location of the antenna. Antenna is a physical entity. It can be a conductor, a physical conductor or a dielectric. So if you consider a finite length conductor, then over that finite length, that you can define, that you can divide into many infinitesimal lengths. So those from each infinitesimal length, the fields will contribute. So since the fields will contribute, so they will be nearly in phase from each point. They will be nearly in phase in the far field. There will be constructive interference from each point, each of these points. So that is the cause of the antenna, cause of the main lobe. For constant phase source, we require in-phase arrival in the direction normal to the antenna. The pattern gives you maxima because if they are in phase, then there will be constructive interference. Constructive interference gives us the maximum. So this is about pattern. Then this is about field pattern. Then there is something called power pattern. Power pattern is more popular compared to field pattern. This is a popular alternative to radiation pattern or field pattern. This is angular dependence of the power density. This depends on P. P is the power density. P theta phi or S theta phi. S is pointing vector. For example, if we have a Z-directed source, then we know Hp is equal to eta into E theta. Then PR or SR, the power or the pointing vector, that we can give as 1 by 2 E theta Hp star minus, which is equal to eta into E theta absolute square. So P theta phi is equal to F theta phi square. Because P theta phi is equal to F theta phi square, because F theta phi is given by E theta. E theta gives you F theta phi or the field pattern. Now you can see P theta phi is equal to F theta phi square. Therefore, P theta phi is the power pattern is the square of the field pattern. Now when you when we use power, usually the unit that we use is decibel. So in decibel, we can say P theta phi is equal to 10 log P theta phi. Decibel definition is this: 10 into log into P and 2 by P1. That is the definition of decibel. So P theta phi in dB is equal to 10 times log P theta phi. That we can write as 10 times for P theta phi, we can write F theta phi square. So 10 times F theta phi square. Now log of x square is equal to 2 log x. So using that, this 10 log F theta phi square is equal to 20 log F theta phi. So P theta phi is equal to 20 log F theta phi. So P theta phi in dB is equal to, if we consider the amplitude part only, then this P theta phi in dB is equivalent to F theta phi in dB in terms of distribution. 20 will be the multiplication of 20 we drop. The reason is simple: the distribution does not change, the amount will change, amplitude will change, but the normalized, if we consider the normalized part, P theta phi is equal to F theta phi in terms of dB. So if you go to dB or decibel, P theta phi and F theta phi are same. That is why when we measure it, always the measurement is in dB. So there is no distinction between the power pattern and the radiation pattern. They are same. The pattern or the distribution is same. Normally, we usually consider the normalized distribution. So normalized distribution is same, whether it is P theta P or F theta P. Both of them are same. Then the radiated electric field, it varies over a sphere centered on the antenna. That is what happens that we saw in the beginning. So you have pushed the antenna at the center of a sphere. So the radiated electric field that varies over the sphere centered on the antenna. For finding radiation pattern, this is how we visualize. This varies only in theta and phi, not in r. We are not considering r because at a particular r, once you fix the r, then we vary theta and phi to see the variation of the electric field over the space. So and this remains constant for a given r. The radiated electric field remains constant for a given r. This is usually normalized with respect to its maximum value. So maxima will be always 1, because once you divide it with its maximum value, then maxima will be 1. That is what is called normalization. So f theta phi is equal to E theta by E theta max. E theta max is the maxima of the electric field. So that is for the theta and phi value, which gives you the maximum. It is absolute value of the magnitude, and it is a real quantity. F theta phi is the absolute value of the magnitude, normalized magnitude, and it is a real quantity since we are considering the absolute part. This is relative to a linear polarization in the theta orientation. So the polarization of the antenna has to be linear in this case. So radiated electric field is relative to linear polarization in the theta direction. This can be referenced to any other polarization state. Instead of linear polarization, we can take any other polarization state. So because any other polarization state can be considered as a combination of properly phased linear polarizations. E theta itself can be complex values. So if E theta can be complex values, then F theta phi can be complex value unless we take the absolute value. So to get it in absolute value, either we set the phase equal to 0. Once you set phase equal to 0, the complex part goes, only amplitude part remains. So set phase equal to 0, or at the same point normalize the magnitude to unit that we have shown. F theta phi is equal to E theta by E theta max. So either how we can do either of these two things. So using that, our interest, why we do normalization? Because the interest is only in relative phase behavior. We do not require exact phase behavior in the measurement. It is only relative phase behavior, so we can always normalize it. So this is one. Or so this is either, or use F theta or P theta. So instead of F theta, we can use P theta. P theta automatically takes care of the complex part. It is always real. So power is real. So that will be automatically taken care of. Then we will come to this part. You can see the figure. On this figure, we have an antenna at the center. There is a sphere. On this sphere, you can see the electric field is oriented from Z towards the H plane. So on the towards the XY plane. On the XY plane, the electric field is from X-axis towards the Y-axis. That way, it is rotating. So it is circulating in the anti-clockwise direction. So on this sphere, everywhere you can see the electric field to be this on this surface of the sphere. On the spherical plane, you can see the E plane, the direction of the electric field and the direction of the magnetic field. The orientation of the magnetic field of the that contains a plane. That plane is called the H plane. The orientation of the electric field that contains a plane, that is called the E plane. So based on this, we define E plane pattern and H plane pattern. The E plane pattern contains the electric vector only. It does not contain the magnetic vector. It contains the electric vector. So electric vector is important in the E plane pattern, although magnetic vector will be perpendicular to this, but we consider the E plane vector. So E vector contains the electric vector. Lies in one of the planes through the Z axis. The planes cutting through the Z axis contains the E plane. Similarly, the H plane pattern that contains the magnetic field H phi. Since it contains the magnetic field H phi, it lies in a plane which is perpendicular to the E plane and cutting across the test antenna. Usually it is the XY plane. In this case, you can see it is the XY plane, that is the H plane, and E plane is in a plane which is passing through the Z axis, which contains the Z axis, and E plane that contains the Z axis is the E plane. When we take the measurement, what we do is, if we are considering the E pattern, then we will consider E pattern for phi is equal to 0 or phi is equal to pi by 2. These are the two chords that we consider, two planes that we consider. These are called the principal plane patterns. The E plane pattern and H plane pattern are called the principal plane pattern. In general, these are for linearly polarized antennas. We consider the E plane pattern or H plane pattern. Principal patterns for single unidirectional beams. That is important. If you consider a single unidirectional beam, then the principal plane patterns are important. So in a single unidirectional beam, what happens is we have got two orthogonal planes. One is passing through the beam point. Both of them are passing through the beam tip, and both are orthogonal to each other. These planes are called the principal patterns. So in a single unidirectional beam, it is easy to define the principal beam pattern. Then we will come to the omnidirectional patterns. In the omnidirectional pattern, the pattern is usually in the azimuth direction, and in one plane, the radiation intensity remains constant at a fixed distance from the source, or at a fixed distance from the antenna in the far field zone. The radiation intensity remains constant. Here we are showing a figure in which you can see that we have a radiation pattern which is a constant, which is a circle, which means it is constant. The radius of this pattern shows you the intensity, so the intensity remains constant since it is describing a circle. Circle has a constant radius, so it is constant. This is uniform here in this figure. It is in the XY plane. For a dipole antenna, the top figure shows you the pattern of an antenna. There are two lobes. Each lobe is like a omnidirectional beam. But if you combine these two lobes, that gives you a figure of 8, which is inverted, which is tilted by 90 degrees. Now in this pattern, you can see that what happens is, if I rotate that pattern, the top pattern, if you rotate it 360 degrees and take a cross section, then you will get the pattern, a 3D pattern, which is like the pattern shown in the bottom. So in the bottom right hand, you see a 3D pattern, which is the same pattern as the top pattern, which 2D equivalent is same as the top pattern. This is very useful. The omnidirectional pattern is very useful, particularly in ground-based application for, like you see your mobile towers. From the mobile towers, there is one mobile tower, but around it, as you move around it on the ground, then everywhere you should get the signal. Unless it is radiating everywhere in all directions around it, you will not get signal in all directions. So on this pattern, the omnidirectional pattern is very useful in ground-based application. The pattern plane is horizontal or parallel to the ground, particularly in this type of radiation pattern. Here we will take a break. Then once we come back, we will consider some other thing. Then we will stop. So let us take a break of 2-3 minutes. Oh.